Dr. Fred DiPiero. This lecture's about combining series and parallel elements. We'll talk about finding the equivalent values for series and parallel resistors, and we'll talk about the process of forming an equivalent circuit. It'd be useful to be familiar with nodes and meshes as we go through this discussion, and we're assuming some prior experience with series and parallel resistances. Okay, it's handy to combine series parallel elements with a wide range of analyses because they could just simplify the circuit before you begin a more complicated style analysis. Here's a case of some parallel resistors. Classic arrangement, R1, R2, R3. Let's talk about how this, the fact that they're in parallel is related to their nodes that they're connected to, and let's also talk about some of their electrical characteristics, given that they're in parallel. Okay, since they're in parallel, they span the same pair of nodes, A and B, shown here. Now, how does that relate to their electrical characteristics? Fill in the blank here. Parallel elements share the same what? Well, they share the same voltage. That's because the voltage at a node, node A for example, up here, it doesn't change across the node. So all these connections from the various resistors to that node must be at the same voltage because there's no voltage change within the wiring of the node. Since all of these resistors span the same pair of nodes, A and B, the voltage across each of these must be the same. As far as current goes, if we had this current I4 coming in here, that current will split out between the various parallel paths going through R1, R2, R3, and the amount of current that flows in each of those paths just depends on the value of each resistor. If we wanted to form an equivalent with a set of resistors, a couple different ways we can do this. This familiar formula here involving reciprocals is a nice one because it can be extended to any number of parallel elements. If you have R4, R5, you just add them in reciprocal form in the denominator. This version is a nice one too. Sometimes we refer to it as product over the sum, a little quicker to compute, only works for two resistors though. Now let's say we wanted to simplify these parallel elements. We get the REQ value, fine. Let's say we associate that equivalent value with a new resistor here over on the right-hand side. And we want to simplify the circuit. So what do we replace the other resistor location with? In the case of parallel resistors, as we're simplifying, we replace this other location with a broken wire, or commonly called an open circuit. Using this sort of approach, you can easily simplify a circuit element by element as you do series parallel combinations. Okay, how about series elements? R1, R2 in series. Let's talk about the interconnectivity involving the nodes. And how does the fact that they're in series relate to their electrical characteristics? Because they're in series, R1 and R2 share a single node C, and they share it exclusively. There are no other connections to node C besides these two series resistors. Fill in the blank here. Series elements share the same what? Series elements share the same current, and that's consistent with the fact that there is no T connection, T-shaped connection here. If there was another connection made here, then, in general, there could be some current flowing through that wire, and we would no longer have identical currents in the series resistance. Also, as far as voltage goes, if we had a voltage VAB across a pair of resistors, then that total voltage across the series resistors would divide out depending on the value of each resistor. The order of elements doesn't affect the fact that they're in series. R1 and R2 are in series here, even though this voltage source is in between the two. Change the order, and then we're back to that arrangement where there's a single node shared exclusively between the series elements. Easy to compute the equivalent, just sum them up, no problem. Now, if we wanted to simplify the circuit after combining series resistors, okay, sure, compute that equivalent value, easy. Maybe we associate that with the resistor on the right, let's say. Now, if we wanted to simplify the circuit, what would we do with the resistor on the left? What would we replace it with? Well, in the case of series resistors, we would replace that other one with a wire. Okay, so R1, R2, that equivalent value goes here, and we then replace the other value with a wire. This is a dual situation compared to the parallel case. Now, sometimes it isn't all that obvious if resistors can be simplified, how they should be simplified. Let's bear in mind also that a pair of resistors may be in series, they may be in parallel, or neither. Okay, so here's an example case. Can this be simplified? And if so, what's the equivalent resistance between points A and point B? Assume each resistor is 1 ohm, for example. Thoughts on that? Well, one trick you might use is to propagate the label of the nodes across the extent of each node till you get to are able to label place a label immediately next to a given component, such as these resistors here. So let's do that. So you have this B labeling the endpoint of the node down here. We could trace through the extent of the wires associated with that node and put B labels next to each of the resistors that are associated with that node, like this. So we have B coming along like this. Now we have B labels here and here. Same thing with A. Go ahead and put an A label next to each of the elements that are associated with that node A. Okay, so if you do that and then take a look at it, hang on, what are we seeing here? That resistor goes between A and B. That resistor goes between A and B. So does that one. Since all of those resistors span the same pair of nodes, they must be in parallel. And if each of these was 1 ohm, you have 3 of them in parallel, the net resistance is going to be 1/3. And more generally, anytime you have a combination of resistors with the same nominal value, and if they're in parallel, let's say, and there are n of them, then the equivalent value would be the original divided by n. So that trick of propagating node labels can sometimes be helpful when trying to identify which resistors might be in series or parallel if you don't have a combination that is immediately obvious visually. Okay, so in this video we talked about finding the equivalent values for series and parallel resistors, and we talked about how to form an equivalent circuit. One takeaway to remember is, sometimes a given pair of resistors may not be in either series or parallel, so they can't be combined.